Hello and welcome back to the Enterprise Universe channel with Dr. James Stoker. Last week we talked about RESPR technology with a quick introduction there, and today we're going to talk more about RESPR features and functions, which is actually really important because RESPR is a really revolutionary technology, and understanding at the next level down what it can actually do to solve real-life customer problems, I think is really fascinating. But before we go there, Dr. Stoker, do we want to chat for just a quick to catch people up on what RESPR stands for and what all this RESPR technology is all about, just at a high level, before we talk about more detailed features?
Thank you, Eamon. That sounds great. We touched on a lot of stuff last time, and RESPR stands for Regional Earth System Predictability Research. It's my first company that I started back in 2002. And not until 2004-5 timeframe when I actually thought some of the data deficiencies were really not reasonable to produce products for my end users. Mm-hmm. So because of my purpose, even though I wasn't defining that in that manner at that time, but internally I knew what my purpose was. Spreading goodness through innovation as it is now. We talked about that a lot. And because of that, I would not be able to give them a data product that had such a big hole. So the whole and realization of the whole was the central point for the Stoker method. So once I realized what the deficiency in the weather and climate science was, that is data gaps, I wanted to do something about it. So that's when I started thinking about what else we could do. And I realized, as my computational fluid dynamics background really prepared me to understand these things in that system level, that state variables, the so-called variables that we observe, are not telling the whole story as far as how they are shaped constantly. And there is something else that take place, like the physical processes, more importantly, the interactions among those processes on a constant basis, every second, every minute, every hour, and so forth. So once I realized that, I wanted to understand how I could enable them within the models using the gradients that are available in the coarse resolution data. So that really led to the Stoker method. But of course, that's still an idea at that point. Right. To implement that within a computer code on a computer system. Back in 2004, actually, I built my own Beowulf cluster from scratch, getting the parts, hardware parts, and putting them together and massaging the codes, and actually wrote my own cluster management software at that point in 2004. And then
so beating VMware to it there, Dr. Stoker, if you had to put that on the marketplace, maybe.
I could have. So, one of those things that I enjoy doing too, because I needed to customize my codes. You pointed out, you asked about serial code versus parallel code. There are lots of issues or dependencies on the architecture. So you have to understand the architecture to be able to take advantage of the type of code that you're using. And again, this all leads to a lot of different backgrounds that you need to have to be able to produce any decent and accurate and more reliable data. And that's why I was saying it's a tall order for a lot of people that are doing computing. And I'm not discouraging them, but they have to be aware of all these fields and how they have to master some of these fields to be able to do some of these things. But remember, even the way we ended up, the discussion was, never lose sight of the primary goal, that is to make your customers' lives better. That really unravels everything else. As for me, the philosophy, my personal philosophy of getting the best out of your talents and hard work in service of others, your customers. So it kind of starts there with the philosophy and leads to all of the 9 fundamentals I try to follow myself, but I'm also offering them. But you can see the tie back with my technologies. For example, the Delta concept, which is really nothing but the Stalker method. Stalker method really is about finding the delta, the example that we used, 79 degrees at location B, as the actual measurement, but the current methods are giving you 60 degrees Fahrenheit with the 19-degree delta. What do you do? First, you have to realize there is one. And second, how do you fill that? That's what the Stalker method and the platform is about. So I tie everything philosophically, but not on a practical level too. This is not a philosophy that people really feel good about and write about and talk about. No, this is actually practical philosophy to really create the value for our customers. I think this segment, we need to think about the product features the RESPR technology offers to different sectors, but I think I want to touch on at least 3 of them on this call, in this segment.
So why don't we just dive into that then? Why don't you just outline the 3 segments that are the main customer problem areas that RESPR addresses, and then maybe we can just jump into the first one of those and have a discussion about the problem, and then about how the RESPR technology actually addresses those problems.
Sure, Eamon. So I'm thinking renewable energy, wind energy, actually when we started talking about, in a decade or so ago. So I think that's a good segment to talk about. And then I want to talk about agriculture, which is really a key industry globally for us and for the technology to help. And then I want to talk about this weather modification, again, related to water resources and water management that I have been guiding some folks over the last couple of years, but maybe since 2004 on and off too. So I will really touch on those 3.
So just as an example, there's been recently a lot of problems in China, and like this may be related to all 3, but there was a lot of problems in China over the last month or so with flooding, and the fact that the Yangtze River was over flooding, and there was even talk of the Three Gorges Dam collapsing, and there being a black swan event there that could, really be devastating for China. How could RESPR technology in any way, shape, or form be of help, for example, to the Chinese government with relation to, could they have maybe had better notice of the fact that there were torrential rains coming, or could the RESPR technology work at that kind of scale for a country like China?
It does, even one of the neat things about this technology is the lead times to your severe events.
Yes.
Currently using the current methods, the lead time is shorter and shorter, maybe minutes to maybe several minutes, but you could actually extend that lead time by having this robust simulation capability, maybe extending it to hours and days and so forth. Yes. So that's one of the key benefits.
It would have seemed to me that, river management and, draining the river to create more capacity, if you had a bit more advanced notice of the flooding, you could perhaps have done a better job of reducing the stress on the dam, for example, in China. So it feels like every day we're getting more and more examples of quote unquote catastrophic events. Well, surely if we can do anything to get a better prediction going, we could avoid untold human misery, or even, something as catastrophic as a Three Gorges Dam failure could be averted. So that seems to be a huge problem area. Is it realistic though for the RESPR technology to be used at that scale, like at the scale of a continent, like or at the least of a large country like China or India or something like that?
Oh, it is. Actually, I want to apply RESPR technology globally, even over the oceans. So the only disadvantage of using RESPR technology, Eamon, as I mentioned before, and it maybe a couple of times, because it's really key point to think about, is the cost of computing. So once we overcome the cost of computing and focus on the benefit, The
Yeah, well, it's
benefit
probably
to
a lot less than the Three Gorges Dam collapsing.
absolutely, not
So,
even close.
not
So
even close.
loss of life and damage to
Yeah.
property, yeah, there's no doubt about it.
But
So
I've found it kind of like horrifying that there could even be the smallest chance that such an event, even if it's hyperbole, the fact that it's even a possibility is somewhat shocking. And I just wondered how far in advance do you think, like, how far in advance could RESPR technology truly improve accuracy? Are we talking days or are we talking weeks in terms of how far out it can predict or it can be used to do like reasonably accurate predictions? And how does that compare to what people do today?
okay, so let me give you a couple of broad points that we covered last time, and I want to make sure we're setting the expectations right. Okay, so the Stalker method and the entire computational fluid dynamics solutions, they fall in the category of what are called approximate solutions. So
Right.
we're not talking about analytical exact solutions where the error is zero, the accuracy is 100%.
Yeah.
We're not talking about that. Such solutions, that analytical solutions, are only possible in simple systems. They're not available
So
in the
they're not
system.
deterministic in that sense. There isn't a known end state for highly complex systems. There's only a spectrum of potential or possible end states. Is that kind of what you're saying there?
Right, the accurate solutions, the analytical
Yeah.
solutions have exact solution
Right.
with zero error and
Right.
100% accuracy. We're not talking about that. Because
Right.
the system is so complex, you can only do approximate solutions, but with the current science and the methods available, relying heavily on the state variable observations, you're so off from the potential accuracy that we could gain through the Stalker method and the RESPR platform. So that's really what we're talking about. So I don't want people to falsely think about we're
Yes,
talking about
sure.
100% accurate solutions. That's really not what we're talking about. But huge improvement over the current methods
Right.
because of the limitations that they are operating under, and we are lifting those limitations through this method.
So we could get like weeks ahead of these events versus days or hours where we are today. Is that a fair statement?
Let me address that. I think it's a great point. The way that I do is improving the initial conditions of a forecast.
Right.
So I'm actually not going to forecast from 0 to 6 months like most other computing approaches do. So what I'm trying to do is within that 6 month forecast, I'm improving initial conditions all along for the 6 months. So that's really why it doesn't matter if you have a 2 year forecast, give it to me. I will make it better through my method. It's really not about myself doing a 2 year forecast, but improving a forecast that's 2 years, which is really worse. There's nothing there you cannot actually rely on, but I can make it reliable because I'm introducing the underlying physical processes all along the way. That's why, relatively speaking, a, a 2 year forecast from the current method versus my 2 year forecast would be so huge, night and day. And I'll actually come back to the example we were talking about, uh, an interpolated value at location B of 60 degrees Fahrenheit, where the actual observation was 79 degrees Fahrenheit. That delta you are unable to bridge using the current science and methods, but the Stalker method would really improve going from 60 all the way towards 79. It could be 70, 71, but that applies to any band of forecast horizon, Eamon. So far I have attempted a 6 month forecast for a wind farm in Texas. And I reluctantly projected what my errors might be because nobody actually attempted a forecast at the resolution that I have. So I was giving them best case scenarios, but when the results came back, I was actually outdoing my own projections.
You were better than you expected. So, but the RESPR method isn't for hurricanes and stuff. It's more for it doesn't really take into account like those kind of black swan type of events or unpredictable. It's more for like, is that a true or not true statement? Or if you, for example, had a big enough model that took into account like West Africa all the way over to Florida, you could actually account for hurricanes? Because I guess my impression was that it wasn't really about that type of forecasting. I guess my impression was more about, you know, so anyways, it wasn't really about that.
Actually, it's not a true statement, no. Eamon. So let me tell you what happens in the weather climate world. Yeah. So you go back to periods like maybe 30 years from today, 30 years up to this point, past record, right? And then today it's current conditions now versus tomorrow, week from tomorrow, 6 months from tomorrow. That's forecasting. So those are the three modes that you have to think about when it comes to weather and climate: past data, current conditions, future conditions. Okay, RESPR technology would be able to do all three relatively better than any other approach that's available, because those approaches are limited by the current science, and the deficiency I found is within the science itself, not within a method.
So the underlying, like, so there isn't, I just had the impression that in a hurricane you're getting non-linear effects that might be hard to model. RESPR could still deal with those types of kind of, you know, crazy kind of wind speeds and torsional effects and all those kind of updrafts, and so you could still model those with the RESPR.
Absolutely, but there are some additional things that have to be done for the application. So here is in that spectrum of time I talked about, back periods, current time, and future. Hurricanes fall within that 1 to 7 day period. Future. Yes. Okay, so that, you know, it could be next day or next 7 days. That's your window. If you are able to forecast that window, you will be able to capture hurricane structures and movements and everything else. But here is one thing that I have not done, and it would be fairly easy for me, relatively speaking, to do this. I have to implement the Stalker method in the oceans.
Right.
Ocean as a fluid separately, and then couple the oceans with the atmosphere. So those are the things that I have not done.
I would imagine that that the data is sparser over the ocean too. There are less data points. Is that a true statement?
It is, especially the depth of it. You know, most observations are on the surface with buoys and so forth. You will still have the same. I cannot give you a number on what it might be, but I would probably say it's close to 10% or sparser than that. So absolutely. But with my method, with the state variables within the oceans and the gradients that are available, I will be able to enable the processes within the oceans, and then couple them with the atmosphere, the overlying atmosphere that I already have done. So that coupling has to take place for me to be able to do a great job in hurricane predictions.
So one of the things that seems a little bit, you know, for the layman like myself. So when it gets to, you know, climate change and radiative forcing, and the idea that there's more carbon dioxide in the atmosphere, let's say this year than next year than the year before, does the RESPR method also take into account that idea that there's a net change in the atmosphere's, you know, retention of heat? Is that a part of the model as well? That where you actually calculate how much heat's being retained by the atmosphere due to reflection but due to the greenhouse kind of effect, so you can actually get a real solid handle on how much heating delta kind of heatings going on in the atmosphere. Is that true? Like you understand where I'm going? In other words, last year's hotter than this year because there's more radiative forcing due to per square meter or whatever, because the carbon dioxide is going up and it's trapping more heat. Is that something that the model takes account of?
It is, Eamon. One of the things that we have to understand about the Stalker method-based RESPR platform is that it's going to give you a robust virtual laboratory to test some of these scenarios. Like, for example, if you double the carbon dioxide, what happens? Right. Because of the limitations I already point out about the other models, that doubling effect is really not representative of anything, because you have so many sources and sinks that are not really taken into account in the current approaches.
And I think that this is why I think I'm trying to point out the complexity of the RESPR model, that all of these kind of different factors are actually factored in, such as the carbon dioxide and the radiative force. Like, there's so many physical processes there. We've already named a bunch, that it seems like, the other one that I often think about is the topology, the fact that, if you've got a mountain or you've got a valley or whatever, how does that factor into the model?
It factors into all of that, Eamon. But let me
so it's a lot of complexity there.
No, yeah, but let me answer this. I think what you're looking for is this, and it's an important factor. So let's say you double the CO2.
Yeah.
Okay, artificially in a model. Let's say a current model that has the deficiency of the science. Within that model, you doubled.
Yeah, 500 ppm or something, or 600
yeah,
ppm.
And you double the carbon dioxide, so you got temperature increase globally. So you say it's warming. But what happens is this: when you don't account for all of the physical processes, like what the Stalker method with the RESPR model does, you're doubling carbon dioxide may have a negative impact in the end when you take all of those processes into account. In other words, it may be increasing the temperature, and you say, well, carbon dioxide is contributing to global warming, but it could be going the other way depending on the type of processes that are available.
I think that I read, and again, I read Popular Science and Lad Time at Scientific America, I guess. But there was an article recently talking about the fact that cloud formation is now being, studied as a bigger contributor. Like, the point is that, like, the clouds and the relationship between warming and the clouds is now kind of causing people a lot of consternation, because they don't really understand the relationship between clouds and water vapor and carbon dioxide and heating, and whether there'll be more clouds or less clouds. And I know that your model takes that into account as well, which is the whole cloud formation problem.
Those of us, that's a good question, Eamon. Those of us that are proficient in cloud modeling, like myself, we already knew that that was the case 20 years ago, 25 years ago. We didn't have
it's news to these guys.
We didn't have to wait for this long to say clouds are important. They are regulating factor on the atmosphere. So that's really not news to us. And that's one of the reasons why some of us that don't belong to the 97% scientists saying it's settled, we would not say you cannot actually settle it until and unless you take into account all of these other things together. Because as you pointed out, in a nonlinear system, Eamon, their interactions are not going to result in the same direction as you think. It may be warming by doubling, though that's not true, because you're talking about global average with lots of different sinks and sources. That's never the case. So you have to be able to robustly model that. And unfortunately, as I point out again, the current science does not allow that to happen, because it heavily relies on state variables that are sparse, And there's no way for the current science to enable the gradients properly like the Stalker method does.
I think the other problem we have too, Dr. Stoker, is that the science itself is so compartmentalized. Even within atmospheric science, I'm sure there's sub-compartments of atmospheric science, the cloud guys and the atmospheric guys and the water guys and the ocean guys. Like RESPR seems to integrate all of those things, or it's a framework for integrating. And my own worry is that we're not very good at integrating science anymore. We're good at parceling things out into little pieces, but we don't necessarily do a very good at putting Humpty Dumpty back together again. Is that true? Do you think that's a part of the RESPR secret sauce? Is that it can kind of take many physical processes from many disciplines and integrate them into a cohesive overall model?
It is, and I'll give you one example, Eamon. I got involved in an air quality modeling study a few years ago, recently, actually, 3 years ago. So in the air quality modeling, there are three different groups, right. Not three different individuals, but three different groups that do the work. There is an emissions modeling group, and there's meteorology modeling group, and there's the air chemistry modeling group. None of the three would have the background in the other two.
Right.
Okay, so because of that, when there is error and there's source of error all the time, they cannot actually, track it, where it's coming right. from. Is it coming from the emissions? Is it coming from the meteorology? Or is it coming from the air chemistry? So when I got into it with the meteorology as the main driver for me to get involved in, I said, this is not how the systems work, guys. We have to do everything. They're like, well, you do it. So I ended up really doing the emissions and found a lot of issues there. And meteorology obviously was something that I already did, but I had to get into air chemistry also. So you are right about not understanding all of the pieces together in a coherent manner and pointing the error sources to somebody else's work. That happens all the time, not because they're mean people, they're just really human beings, how they do it.
Yes. And I've seen this insofar as even in my own career around, they're not using the same mathematical, philosophical approach to the problem. So in other words, it's kind of like one guy's using Newton's laws of physics, another guy's using Clerk's, Maxwell's equations, another guy's using Bernoulli. In other words, there's no kind of coherence and then it's very hard to put Humpty Dumpty back together again because they're not logically integratable because they're based on completely different mathematical underpinnings. So I presume that within RESPR you're able to kind of cohere because you've got you can bring them into your mathematical models and model them as a fluid dynamics problem versus I wonder sometimes, are we approaching many disciplines with the wrong mathematical, we're thinking about it fundamentally the wrong way, based on statistics, for example, or based on very basic linear equations, or based on and not using the proper modeling approach for the problem period.
Well, Eamon, I think that reminds me of talking about this a little bit too. So think about this. It's not a platform-based solution. A platform is only going to give you what you do with it. So who is doing it really has a whole lot to do with what you get out of it. That means understanding the system at a very high level. So what's in the Stalker method? Stalker. That's the important factor in it. My expertise really has a lot to do with how the method is implemented, what the platform does, and that really needs to be part of everything that we do. But let me just tell you, when it comes to the RESPR platform producing data for various industries, you talked about renewable energy, agriculture, and weather modification. There are three, the data production is a very solid, largest piece of the puzzle. Amen. Don't get me wrong. But there are three other layers also as part of the whole package. And the second layer, what I call analysis. When you get the data, you have to be able to analyze. If you don't have the analysis capability, you're not going to be able to take full advantage of the data. That's the second layer. But you have to make recommendations based on the analysis. That's why it points to the third layer, which what I call expertise layer. And that's a critical piece. That's where Stalker, my own expertise, lies. That really brings the best out of the analysis and best out of the data that's produced by the RESPR model. But there's a fourth one layer, and let me finish that, and that is application layer. So you have wind speed, but how do you use it for wind energy? Or how do you use wind speed for agriculture or weather modification? These are the things that you have to develop in application layer. So when it comes to the product features, Eamon, you have to think about all four of those layers working together as a package. Without that, end user
could I suggest, Dr. Stalker, there's also the initial conditions that you mentioned earlier, because presumably if you change the initial conditions, you could get different results. Is that, and what I mean by initial conditions is there must be some kind of setting up of the model and based on, you know, is there that idea of, you know, we'll run it, we'll tweak the parameters and we'll see what we get versus we tweak so you could get different outcomes based on tweaking the initial conditions. Is that fair? Is that another?
It is fair. When it happens, let's not say it's fair or not, but it does happen. There's a whole science that people have built on called chaos theory, where you change your initial conditions or perturb them to get different forecasts, and then you figure out, you know, what the error band is and so forth. I would not recommend any of that. All of their work is a waste of time, but that's the best they could do because, you know, you're trying to understand the system without really understanding the process enabling capability. Right.
So on the application end then, I guess, so therefore, if I understand this correctly, when we look at agriculture, renewables, and weather modification, they're all really applications. The underlying first three are all the same. We're just basically building application layers on the back end of the Stalker method. Is that a fair statement?
It's a fair statement. Actually, I don't even think about wind energy when I'm simulating for a project. It is, I simulate 30 years of data for the project location, back periods up to current year or current full year. And then you have 30 years of data using the Stalker method, backfilling with the process enabling capability. In other words, bringing that interpolated value from 60 degrees Fahrenheit as close to 79 as possible. That example is only for temperature, but it happens for wind speed, wind direction, humidity, you name any variable, solar radiation, precipitation, all of them have the same delta without the enabling physical process enabling capability of the RESPR model. You have that large gap. And that's why I don't even think the interpolated values are considered useful at all, because they're not. But once I develop the 30-year data record for the wind application, I go into analysis layer first, how the data are doing, if I needed to understand something else, and then use my expertise to recommend how those data are pointing to the site, whether the site is optimal for production, what type of wind turbines are optimal for that location. Those will go into the application layer, Eamon. And I will tell you a little bit about your correlation idea that you talked about yesterday, why I say no to that. But let me see if you have any questions on that, going from the fundamental data sets to the application layer.
No, I think that makes sense. I guess one of the things that I don't necessarily understand is how localized weather is and the degree to which you need a global versus a local data set. So for example, just this whole kind of idea that maybe we've got a looping jet stream and it would be very hard to predict that just from a local data set. And how often is it that we have disturbances coming in from outside your data set? Do you know what I'm saying? So in other words, your data set is here, but there's something happening out here that you don't know about that's coming in and having an effect. You couldn't possibly predict that from your data set because it's outside. It's like it's outside your event horizon, if you will. So how big does your model have to be to basically reduce the risk that something outside of your viewpoint could actually impact your model in a significant way? Do you see where I'm kind of going with that?
Yeah, I know where you're going with it. So what happens is this, Eamon, you have to understand the application.
Yeah.
So when you understand the application, the timelines that you're talking about,
you can create the data set.
You have to be able to expand the domain as much as needed. But that's one of the things when you set up the model, you have to understand what's influencing or could potentially influence your location and the solutions. That's part of setting it up. And that's why people do a lot of iterations without understanding what they're looking for. So without the proper understanding, it's not easy for anyone to set it up.
It didn't seem obvious to me how big a data set you need to model a situation, because if you don't know, it's like 1 mile, 100 miles, 300 miles, it's not very, it seems like that's a decision you have to make, or it's not true. You have to know what you're doing to know how big an area you need to model to solve a particular problem. Do you think in the future you would ideally just model very large areas and then have multiple applications running off the data sets? Because that seems like it'd be more efficient to model very large areas and then have multiple end rather than modeling per application. Or do is that a true statement that would be better?
It is, but one important factor to consider, Eamon, is what is your application horizon? So depending on the application horizon, you don't have to expand it all out to globally to be able to do what's going on at your location. But having said that, you need to have certain domains so you don't have any spurious influences on your solution domain. And that's one of the things. But ideally, Eamon, where you're getting at is when I talk about global mapping, in the next segment, we will touch on that for countrywide maps and so forth. Setting up the model the way that I have developed for the atmosphere, but also couple that with the underlying oceans, that doing it globally is the way to go to really robustly get all of the data as accurately as we can.
Yeah, and then the application layer is just an add-on to that. That would intuitively make the most sense to me, that you would do it at a resolution that makes the most sense for the applications that you are using the model for. The only problem being just immense complexity of modeling the globe, and all the interacting physical processes. That would need a big computer, I'm guessing.
Well, there are ways to minimize that effort simply for a local application, but it really depends on the application. But one of the things that I want to point out, you were saying this the other day, last week, is fine-tuning the model.
Mm-hmm.
Fine-tuning is really, it has a negative connotation. You're trying to get an answer that you're looking for. That's really not what I do. What I do is understand the model from the mathematical setup and the physical representation of it and the assumptions. If there are any inconsistencies in any of that, eliminating those before you produce a solution is what I do. Not, factor this or do this or improve the initial conditions or perturb them. That's all exercise that you can call fine-tuning, but that's really not what I do. So refining your understanding and getting a better solution is not the same as fine-tuning.
So in the context of, let's just take a hypothetical state, we'll just say Wyoming or North Dakota or whatever, it just doesn't matter, or New Mexico. It would be theoretically possible then, I guess, to run the model for like a reasonably big area and then basically use that for all of the use cases. So we could use it for weather modification in Wyoming. We could use it for agriculture in Wyoming. We could use it for energy production in Wyoming. Would that be the optimal kind of use case where we find customers who wish to solve, or is that how you envision using the thing, or do you envision, because it may be difficult to sell this to an individual, like an individual guy doing an individual solar plant. It might make more sense to use it more strategically to figure out what's the what's going on in North Dakota, what's the optimal layout for renewable energy in North Dakota, and then basically work backwards from there rather than trying to run a forecast for a guy that might have put the plant in the wrong place in the first place. Is that a true statement? Or
it is definitely more efficient doing the statewide or globally, actually, as we talked about. But we could also provide solutions to project-specific locations for a lot less cost. It's not the best way to do it, but it's the cost issue. So we can provide that. But one of the things I want to point out, Eamon, you're right about the generic data produced by the RESPR technology. Once you have the 30 years of data robustly developed for your state, let's say Wyoming, you could use the same data in the application layer for various industries, as I already pointed out. But what people do now, Eamon, is because of the fact that they're not really coupling the whole thing and they're not enabling the underlying physical processes. So they give you wind forecast from wind data. They give you solar data from solar data, or precipitation from precipitation, all along knowing that the atmosphere doesn't work like that. The atmosphere interacts with every other process that's influencing wind, temperature, or solar radiation, or humidity. They're all interacting with one another. Because of the inability of the approaches, they give you wind based on wind and solar radiation based on solar radiation. But I'll tell you, I want to highlight something that's done in the renewable energy field, and you're very familiar with it. And your correlation idea probably came from there, and I want to point that out. So what they do in wind renewable energy project development, Eamon, they measure wind speed at the location that they want to build the plant for like 1 to 2 years. Okay, let's say 1 year. So what they do is this, but they want long-term 30-year, 40-year variability. How do they go from 1 year to 30-year, 40-year variability? This is what they do. They find the nearest airport that has 30 years of data record. You know, the airport reported, you know, missing values and all of that. Even if you say that's perfect data set, 30 years of it, and you got 1 year at your location. They pick the same year that they measured at the location of interest with the airport data, and they correlate those two and figure out what the correlation factors are for that particular year. And then what they do is use the same factors for the rest of the years to estimate what the wind speed might be at your location.
Right, sure.
Okay, and it's called measure, correlate, and predict. That's what they call, and they used to brag about that, and it used to really bug the heck out of me. And I'm like, you're going to invest hundreds of millions of dollars based on this method? The answer was yes.
Yeah. That is funny.
So correlation is the what I'm trying to say is there is no correlation in the real atmosphere.
It's not science is the point. It certainly isn't. And that is, yes, and that's where it's kind of like, that is a little bit of a frightening story, but it doesn't surprise me. honestly.
So
That's
in
how
the real atmosphere, Eamon, there is no correlation. The correlations only are, you know, that's a simple way of representing the complex atmosphere.
right.
There is no way
Well, there
because
was. I have a good friend who worked for a large company in the Scandinavia, and they had a lot of problems with their wind turbines because they didn't take into account the peak winds. So, in other words, they did what you just said, but they found that the problem was the wind at the very top versus the wind at the bottom, and the difference. The problem was there was a torsion effect due to the fact that if it's blowing really hard at the top and it's blowing less at the bottom, there was a it was putting a kind of a this type of, and they hadn't designed for the fact that the wind that the wind turbine was having a lot of this type of motion. So you got the round, yeah, I get that, but I didn't realize that the delta between the forces were so big, so it was bending back, that they were being bent backwards because the wind was so much higher at the top than it was at the bottom. And they all were failing about 10 years earlier because, as you say, they had the one measurement, but the problem was that the peak, it was the top to the bottom was the problem, and the fact that like one night a year it went like crazy. There was a huge delta between the two, and and they hadn't engineered for that when they built the turbines, and it caused a lot of problems.
When they designed the wind turbines, perhaps they estimated a 10-year or 15-year lifetime.
Yes.
Such a wind regime could make the lifetime shorter by almost 70%. So
yeah, it wiped out the gearboxes and stuff because they didn't realize that they were going to be subject to this much stress and the peak stress type of thing, and that didn't show up in their data. Didn't show up in the data sets, as you say. So as you say,
what happens when you do wind. When you do wind based on wind, Eamon, and also without taking into account all of the other atmospheric variables and processes and interactions. I harp on interactions because that's more important, as important, if not more important than the processes themselves, because their interactions are the ones that are responsible for all the variability that you see in any of the measured variables like wind speed and temperature. So, just want to give you one additional point about the products. If a project developer came to me and they said, Dr. Stalker, we don't mind the cost, whatever cost, but we want to do the best job we could, then I would recommend to them 30 years of back data, and then do the application layer, and then do the design. And then based on the design, when they build the project, we will be offering them daily forecasts, weekly forecasts, monthly forecasts, and even up to 6 months in advance, which is what I tried. So they have to think about this as a two-phased project where we're building the data sets for the location and then doing the design and then operating the project more efficiently on a daily basis, on a monthly basis.
Right. That makes perfect sense. So so you get some future look, and but you basically, I guess a lot of the concern though, Dr. Stalker, is that there's so much degradation going that prediction is becoming harder because we got so many simultaneous things like deforestation and pollution and aerosols. Like there are so many things going on, and the rate of change is increasing. It's very hard to be accurate about what's going to happen in 10 or 20 years here with the climate. It feels like nobody really, like, I guess from a little bit, and I guess I'm changing track a little bit to the just the concern a lot of us have out there is that we don't really have a handle on what the hell is going on. And the fact that we don't know what's going on is a cause for worry, just irrespective of, there just seems to be has RESPR the opportunity to help us with those kind of global strategic type problems as well?
Absolutely, Eamon. That's one of the things that I built the technology for. So overcoming those deficiencies really is the way to go. And right now they cannot actually do long-term prediction. It's the science does not allow that, but they end up doing it anyway. But there is no way one could go from the initial conditions to 6 months the way they do now. So the only best alternative is to break it up into segments like I do and improve the initial conditions all along that the forecast period. And if you want to do 20 years, I would still be able to improve that, relatively speaking. So I would not eliminate it completely. In other words,
that's impossible.
I would not go from 60.
But you get us within a tighter band than the 2 to 7%, 2 to 7 degrees warming, which is where we're at right now. We'll warm by 2100. We'll be somewhere between 2 and 7 degrees warmer than we are today. It's kind of like that's kind of a pretty large spectrum of uncertainty. To be honest,
it is, and that's because the current science and the approaches are not able to give you that type of solutions.
And so I guess
I would certainly be able to help with that, but it has to be done on a global basis. And I do have to say, Eamon, when I'm doing it on a global basis, I do have to implement the Stalker method in the oceans and then couple them with the overlying atmosphere.
So, I just wanted to say that I just think that it's not like, yes, there's applications, and we haven't talked about the weather modification, and I think that's worth its own session. We've kind of touched on the renewables. We haven't really talked about the agriculture as applications. We've talked about the core model. I just think it's important for people to understand that those applications are still, they're industry level, but the method can also be used for like strategic issues that have got global and societal implications. And that's one of the things I'm most excited about the Stalker method is, yes, I'm excited about, using it for these very important applications, but I'm most excited about using it to be strategic about how our relationship is with the global climate and as a society staying away from the danger zones and charting optimal paths to meet civilizational goals within the constraints of our ecosystem. So I'm not about going back to the Stone Age, but I do feel that nobody really has a method of understanding what's possible and what an optimal path for our civilization might be within the context of our ecological constraints. Does that make sense, Dr. Stalker, what I'm saying there?
It does, and I want to really touch on this for the global mapping segment next time, but since you brought it up, I want to give a little bit of an idea about this. So if you go to a country, let's pick a country, UAE, and if you go to them and say, hey guys, do you know what your natural resources are quantitatively, meaning wind resource and solar resource and your precipitation, their answer ought to be no, but sometimes they give you an answer like we do because we got measurements and so forth. But when we actually make them realize measurements are not the ones that are going to give you those answers, once they understand that and how the Stalker method is going to enable the underlying physical processes to improve that understanding, then they would say, no, we don't understand it, but we do want to understand our resources quantitatively. Because unless you understand your resources quantitatively, Eamon, you're not going to be able to use them optimally for your.
Yeah, that makes perfect sense.
And that's really what I'm going to talk about on the countrywide mapping efforts and why that's needed. But falls from that effort the ability to understand those three potential scenarios I talked about. It's warming, staying the same, or cooling, and we will be able to put quantitative understanding on all three of those scenarios, and then use your mitigating strategies. Like, for example, you say cut down all of your air pollution.
Yeah.
Great. But what if that doesn't do anything?
Right.
So
Make things worse.
I could make it worse. So those are some of
that's
the
like
things.
this little thing of, shut down all the coal plants and make it worse, because coal could be having a significant masking effect on solar radiation or something such thing. I've heard talk of that. So I feel that charting a safe path back to sustainability isn't obvious, because like doing the right thing at the wrong time could make things worse. And I really feel that that's a real problem, is that like I think the example is, if everybody jumps in an electric car, I don't think that's going to make things necessarily better, because we're digging up a bunch of precious minerals. It takes 10,000 I don't know, so how many 10 tons or 20 tons or whatever it is of carbon to make the car. Half the electricity is still coming out of coal plants. Buying electrical cars in that context doesn't do much actually for us.
It's a marketing ploy for sure that has no real bearing. But here is the key thing, and I will touch on this on our next segment.
Especially if you build cyber trucks that are huge with big tires, like that's not ecologically. It's kind of a joke, really.
No, so here is the meat of the approach and all of the stuff that I'm talking about. It's easy for anyone to go tell a country to shut down their power plants, and problems would go away. You have clean air. That's really not a viable solution. The best solution in that case is to tell them, look, you could keep your economic activity level the same, but by doing these things, you are going to minimize your pollution footprint.
Yes.
So in order to do that, achieve both, you need to have clearly well-defined, deeper understanding through the science and technology. Once you have that, you can achieve both. And that's something that I would talk about in our next segment.
And I personally feel, Dr. Stoker, weather modification has to be a part of the conversation now. Because we're already modifying the weather, whether we like it or not. We're doing it through our behavior. So it's kind of like, hey, human activity affects the weather. So when we talk about weather modification, we're already doing it. We're just doing it ignorantly. So we better get into weather modification that's smart, because civilization modifies the weather. Hello, So when people say, oh, no, weather modification, I say, we're already doing it. And we can't go back to the Stone Age. So we've got to actually understand to the degree that we can do smart modification that's beneficial versus this, because we're ad hocing it right now. We're doing uncontrolled experiments on the atmosphere. And I don't think that's necessarily the right path for a sustainable civilization or any kind of a smart civilization. We need to recognize the fact that civilization modifies the atmosphere, and that we need to do it in a productive way, because you won't have civilization if you have no modification in the atmosphere. You probably won't have civilization. So I don't know if you agree with that, Dr.
I agree with you. The key phrase I used there, Eamon, before you do cloud weather modification, you need to improve your understanding. You have to elevate your understanding. And the elevation of understanding is not possible through the current science and the limitations it has. And that's a paper that I actually wrote, and it's been accepted in the Journal of Weather Modification. It is something that hopefully the weather modification folks are going to pay attention to globally going forward. But the current methods of relying heavily on state variables for analysis and forecasting, that's not going to allow them to use weather modification techniques
Because you need to understand it at so much more a fundamental level to use those techniques effectively. Otherwise, you're essentially playing with matches. I think that's the bottom line. So, Dr. Stalker, we've been at it for an hour. I hope the audience is stuck with us. It's fascinating conversation. I always get, I think there's so much more to explore in our next couple of outings here. Any last words before we wrap it up for today?
Yeah, Eamon, I think it has evolved into a pretty good discussion again. I want to just say the RESPR technology and my approach is useful, actually significantly beneficial to agriculture also in terms of determining growing season, last freeze, and how to manage your fertilizers and pesticides and things like that, and the crop output. So those are some of the things that they would be able to manage.
So maybe we can have a quick chat about that at the beginning, because I don't feel like we've gotten through all of the use cases and really explored them thoroughly. So maybe we should do a little bit more of that and talk about who should be interested in RESPR at a little bit more granular level. So maybe for the next time, everybody tune in and we'll talk a little bit more about the use cases, and we'll get into global mapping, which I think a lot of our audience are going to be very interested in, which is the strategic use of RESPR technology. So at the planetary level. So thank you, Dr. Stalker, again, as always, for taking the time with us. And we will basically look forward to seeing you on our next episode.
That sounds great, Eamon. Thank you.